Hello and welcome back to Math Class in Session. Today, operations with algebraic vectors in R cross R. We're looking at two space today. Standard basis vectors in R cross R. Well, what's a basis? A basis for a space, like two space, a basis for a space is a set of vectors such that any vector in the space can be expressed as some linear combination of that basis. In other words, the basis covers every single vector in the plane as a linear combination of basis vectors. Let's see what all this means. The standard basis vectors for R cross R are the unit vectors I, 1, 0, and j, 0, 1. There they are, I and j. Now, any point in the entire two space can be expressed as a linear combination of I and j. All vectors in the plane can be expressed as a linear combination of the basis vectors. For example, the vector 2, 3. So this is a vector. This black line is a vector, and it's the vector 2, 3. It goes to the point 2, 3. It's the position vector. It's actually, this is called a linear combination. When we add a multiple or subtract a multiple to another multiple and put them together, we combine them together, it's called a linear combination. And so if we take two i's and three j's, it's the same as vector OP here. So AB is being expressed as a linear combination of these two basis vectors, two i's plus three j's. And it's real simple. That's probably why they chose these to be the standard basis, because any two non-collinear vectors could form the basis of the space. Any two non-collinear vectors are such that any point in the space can be expressed as a linear combination of them. But we're going to focus on these standard basis vectors, I and j. Write the vectors using I and j. Well, there's a vector. It's 0.5 minus 7. It's the position vector associated with that point. Well, it would be 5 i's minus 7 j's. The point minus 2, 0, or the vector that goes to the point minus 2, 0, minus 2 i's. This one, minus 13, minus 12, well, minus 13i minus 12j. You'll see that it's not real difficult. Example, write the vectors in component form. Well, this is component form here. So in other words, we want to take a vector and go back to that form. So I plus j, well, that would be 1, 1. 1i plus 1j. It's just the coefficients on those. The vector 3i minus 5j. This is a linear combination of vectors, and we're going to express it as a single vector. It's just 3 minus 5. Okay, how about this one, 37j minus 2i? Well, be careful, be alert. It's real simple, but put that minus 2 first. Minus 2, 37, because it's minus 2i, and I comes first. Adding and subtracting algebraic vectors. Oh, what a wonderful thing this Cartesian plane is. We can add and subtract vectors so easily. Thank you, Mr. René Descartes. To add or subtract algebraic vectors, one simply adds or subtracts the corresponding components. So vector 1 plus vector 2 is equal to x1 plus x2, comma, y1 plus y2. We just add the x components and add the y components. Let's see this in action. Here's a random vector, say 2, 4, and here's another one, say 5, 1. And let's add these together the old-fashioned way. That would be using, say, the parallelogram method of vector addition. Now, the parallelogram method of vector addition means we create a parallelogram here. So here I have to draw this vector, which says 5, 1. So go over 1, 2, 3, 4, 5, and up 1. So go over to there. And then we have to draw this vector, 2, 4, over here. And notice it goes 2 to the right and 4 up. So let's go 2 to the right and 4 up. Now, of course, it goes there and it completes a parallelogram. And this is what we've been calling the sum of the vectors. And we'll notice that the sum of the vectors goes to the point 7, 5, and 2 plus 5 is 7, and 4 plus 1 is 5. What could be easier than that? We don't have to make parallelograms, we just have to add components. That's how we add vectors. 2, 4 plus 5, 1 is 7, 5. And of course, if there's a minus sign here, we subtract the components. So we can add and subtract vectors like child's play. Thank you, René Descartes. Multiplying vectors? To multiply an algebraic vector by a scalar, by the way, you could multiply a vector by a vector, but we'll do that later. Multiply a vector by a scalar, multiply both the components by the scalar. Evidence of the truth of this. So we've got a multiple of a vector. Well, let's express that vector using a linear combination of the basis vectors. And now we sense that we can just multiply the k in using the distributive property. And now let's put it back into component form. So this would be ki and kb. And we can see that, yes, the k just gets multiplied in there. That's just some evidence. I think evidence is good. Finding the vector between 2 points. Okay, this is significant. How in the heck are we going to do that? Okay, now that is a random point. It's the point x1, y1. I suppose I could have called it P1. I called it A. But the point being that this point could be anywhere in the entire grid, as could point B, or P2, x2, y2. So I drew them here, but they could be anywhere. And what we want is a formula for this vector between any 2 points. A formula for this vector, AB. We want a general formula for the vector AB. Okay, well, let's take a look. That is the origin, 0, 0, and that is the vector x1, y1. By definition, that's a vector x1, y1. It's a position vector. And this is the vector x2, y2. This is OB. So this is OB, and this is OA. Now, isn't it true that if we were to add using the triangular method of vector addition, so it would be OA plus AB, isn't that the same as OB? Yes, it is. OA plus AB, OA plus AB is equal to OB. Now, what we wanted was a general formula for AB. Well, there's AB. So why don't we just take OA, drag it across that equal sign, and we'll have a formula for it. AB equals OB minus OA. In fact, in general, vector AB between any 2 points is x2 minus x1, y2 minus y1. We subtract backwards here. If you wanted AB, you start at B and subtract x2 minus x1 for the x component, y2 minus y1 for the y component, subtracting backwards along this vector. Now, if I took this vector that we just calculated, AB, and I moved it over there to the origin, we could see that that vector was in fact AB, and it's 6, 2, because we can count here 6, 2. So I took AB, dragged it over here, made it, it's actually the vector 6, 2, but let's take a look. That's the point minus 4, 3, and that B point, that's the point 2, 5. If we did subtract backwards instead of doing all this, we just went 2, subtract negative 4, yes, we get 6. And if we go 5, subtract 3, yes, we get 2. So that's some evidence for you, again, that this formula does in fact tell the truth. One last little thing to note is that how long is a vector AB? How long? What's the magnitude? When you see these symbols, these absolute value brackets, They stand for magnitude, the length. How long is that? Well, Mr. Pythagoras steps in and tells us, let this be xy. So therefore, along here would be x, and along here would be y. And so the magnitude, the length of it is the square root of x squared plus y squared, because of Mr. Pythagoras, never far from a math class.